Hello students, today I am going to discuss you about the B plus tree. In last class I am already discussed with you MA search tree and B trees. Here like MA search trees and B trees, B plus trees also followed the property of binary search tree. It is also called as balanced binary search tree. Here unlike B trees, it followed the multi-way index format. In B trees it is followed the index format, but it followed here, but it followed the multi-level index format. Actually in B trees it has variable number of order, but here in the order n, where n is a fixed, here there is no m multi-way orders, that means 4 5 whatever. Here the order is fixed. And also the leaf nodes denotes actual data pointers, and all the leaf nodes remains at the same height. So all the leaf nodes remains at the same height means it is balanced, thus it is called as balanced binary search tree. And B plus trees, leaf nodes are linked using linked list. Here in this example we already seen this arrow marks, these are linked list. It can support, leaf nodes are used linked using the linked list, so it can support random access as well as sequential access. Every leaf node is equal distance from the root node. Every leaf node is equal distance from the root node, like this. Here I already discussed you in the second point, that is multi-level indexing. Multi-level indexing, what is multi-level indexing? Here in our textbook index page, all the chapters page numbers are given here: 1 to 3, 3 to 9, 9 to 15. But here in the multi-level indexing, with the chapters below subpoints 1.1, 1.2, 1.3, and then that 1 2 3, 1 2 3. This is called multi-level indexing. Here already here mentioned the 1 2 3 page number, and repeated first page again and third page again. This is nothing but the duplication. Here the duplication is allowed here. Why? Because of easily understandable and easy to get the page number. So this is called multi-level indexing. Here all the leaf nodes remains at the same height from the root node. Here let me take, this is the root node, and all the leaf nodes are placed at the same height. So thus this is called balanced binary search tree. And it can support random access as well as sequential access, whatever. Why? Because it is linked. If it is not linked, we have to follow this sequential access only. This is linked, so we can randomly access through these links. So every leaf node is equal distance from the root node. Here order is fixed. If order, let us take order as n, then it is fixed, there is no change in order. Okay, so let us know about the internal nodes and leaf nodes. Here there are two types of nodes, that is internal nodes and leaf nodes. Internal nodes may also called as non-leaf nodes. Non-leaf nodes may contains non-leaf nodes may contains n minus 2 number of pointers, that is at least except root node. This is for internal nodes. And leaf nodes, at most it has n. What about leaf nodes? Leaf nodes contains at least n by 2 records. That means data pointers, data, and n by 2 key values. Here internal nodes and leaf nodes. Internal nodes may also called as non-leaf nodes and leaf nodes. Here the leaf nodes are at same level. Leaf nodes is the data nodes here that we can call as key values, and internal nodes are the address nodes. So it at least it has n by 2 number of pointers except the root node, and at most n number of pointers. Here leaf nodes have at least 1 by 2 records, that is data, and n by 2 key values. This is all about the internal nodes and leaf nodes. Then what about the B plus tree properties? What about the operations? Operations, we already know that insertion, we already know about insertion, deletion. Insertion can be done from the leaf node, so it have to be done from the leaf level. This is also followed the bottom up approach like our B trees. So insertion could be done from leaf nodes, and here we already know about the B plus trees property. Here leaf nodes are remain at the same height, and every leaf node is equal distance from the root node. So whenever we have to insert any node, we can directly insert it. If there is any overflow occurs, then what we can do, we have to split it to 2, and then we have to take the one of the median from this splitting node to root node. This is also like our B trees insertion, so that we understand in detail. Here, if a leaf node overflows, split node into two parts. Partition it I equal to m plus I by 2. First I entries are stored in one node. Rest of the entries I plus 1 onwards are moved to a new node. Ith k is duplicated at the parent of the leaf. Actually, I already discussed with the example of textbook. Here the duplication is allowed. So here the address pointers are also present in the leaf nodes. Here the address pointers are nothing but the internal nodes, and the leaf nodes has data pointers. Here in the first textbook example, already first page number is placed in front of first chapter. Like first chapter is BST, so in first chapter, in front of first chapter, first page is already there, but in 1.1 again first page is placed. So this is nothing but the duplication. Here this is the address pointer, this is the main topic, so this is nothing but the leaf node, and this is nothing but the internal node. Likewise, if non-leaf node overflows, non-leaf nodes are nothing but the address pointers which are present above the leaf level, so we have to split into the two parts and partition. Same process again if leaf node overflows, and then we have to split, and when then median goes to the up, and then rest of the entries move to the new node. This is all about the B plus tree insertion, and let me discuss about the B plus trees deletion. B plus trees deletion, entries are deleted at the leaf nodes. Like every node can be deleted from leaf node if the target entry is not present in the leaf node. If it is present in the leaf node, there is no problem, we can directly delete it. If it is not present in the leaf node, other than the leaf node, then we have to search it, and then we have to follow the rules. If it is an internal node, delete it and replace with entry from the left position. Okay, so if we delete it and then replace with the left position, if underflow occurs, there is no node present in the left, So then what we have to do, if underflow occurs, distribute the entries from the nodes left to it. If distribution is not possible from the nodes left, then distribute from the nodes to right. If distribution is not possible from either left or right, then what we have to do, then we have to merge the node with left and right to it. Already these type of examples were shown in B trees deletion as well as insertion. So we should follow that in the deletion of internal nodes, or else in any underflow occurs. If overflow occurs, overflow can be occurred in insertion operation, and underflow can occur in deletion operation. If overflow occurs, then we have to split it. If underflow occurs, we have to redistribute it. Otherwise it is not possible to if it is not possible to redistribute, we have to merge it. This is all about the insertion and deletion. Then let me move for the construction of B trees with an example. Here let me take an example here. So I will show it here with this example. 1 4 7 10 17 21 31 25 and 19. Oh, this is so long. Okay, no problem. So construct or create or insert this B plus trees. So here the order m equal to 4, and then minimum child maximum child, minimum keys, maximum keys and minimum keys. So minimum child can be minimum child, that is m by 2. See here these are the formulas. Minimum children m by 2, maximum children m, maximum keys m minus 1, minimum keys m by 2 minus 1. Here we always take in the ceiling value. This is the properties or formulas we have to check after every insertion. If it is not satisfied after any insertion or deletion operation can be done, that is not the B plus tree. So it have to be satisfied. So we'll take minimum children and maximum children, that is m minus 1, minimum pointers, that is m by 2 minus 1, maximum pointers, that is m minus 1 means 3 2 1 4. Okay, here maximum keys, actually I have missed a point. Here the maximum keys, sorry, pointers are children and are equal, so keys we have to take. So children are m, that is 4, and keys are m minus 1. This is here children or else pointers, these are same. Keys are different. Keys and what we can call data nodes, these two are same. So here the minimum children m by 2, maximum children m, minimum keys m by 2 minus 1, and maximum keys m minus 1. So let me go with our insertion. First we have to go with the 1, insert 1, that is here we have taken m equal to 4, so we have 4 minus 1, that equal to 3 keys. Here these are the 3 divided blocks. Here we have to take the divided blocks. Why we should take the divided blocks? Because it is very easy to understand, so we have to take like this. These are the pointers 1 2 3 4, and these are the keys. So insert 1, then insert, what is the next element? 4. Insert 4. You can take these pointers or else you cannot, it's your wish. If we shown in this picture, that's very good for your exam. Your examiner will consider your effort and give you the marks. You can easily impress with this. Then 1 4 7, the inserted node must be in sorted order, so we can go through this. Then insert 10, so insert 10. Here it is already filled. Insert 10, where we can insert 10 after 7, but it is overflowed. This is the overflow condition. Whenever we want to insert one of the nodes given for the construction of B plus trees to the filled block, so then we have to split. So we have to split with the median. Here 4 and 7 are the medians, so we have to take one of the median, either from left or right. Here we follow either of the case, left or right. Here I want to follow left biased, so the left median is 4, so we have to take 4 to the root, and then 1, and then 4 7 10. Here why we are copying this 4 to here? Why? Because these are the internal nodes, and also we have the property, all the leaf nodes, all the data nodes are must present in the leaf node. So that's why we want to copy this, we have to copy this pointer. So before or else less than 4 or up to 4 are present from the left side, present in the left side, and from 4 and so on are present in the right side. This is the BST property shown here. And then what is the next insertion? 17. Here 1 4 7 10, so here this is a 4. So we have to insert 17 here, but again overflow condition. So I already followed the left bias, so throughout the insertion you should follow it. We must follow the left, not right. Only one can choose for the entire tree. So here the median is 7, so we have to take it 4 7 1 4 7 10 17. Again for the reference, here we have to copy here we already copied here, and then we should link it. And then what is the next node to insert? That is 21. 21 is also how to insert here. Why? Because always for the BST property, highest or else maximum values are always present in the right side, so we directly go to here, and 21 have to be inserted here. But again this is the overflow condition, so we have to take the medium to the up, and then again splitting can be occurred. Again 7, again 10 17 and 21. See here, these are all the reference nodes, nothing but pointer nodes. This can be called as internal nodes and this can be called as the leaf nodes. Leaf nodes are the pointers. Whenever we have to pick anyone from this tree, B plus tree, we should directly go through the pointers. For example, I want to check whether there is 8 or not, 8 is present or not. So we have to go from the internal nodes 4 7 7. So from the right side of the node 8 is present, so we directly go to the 7th 7 8, so there is no 8 present. Or else if we want to go through 11, so we want to check from right side, from right. After 10, 11 may be present or may not. Here 11 is not present. Likewise, searching is very easy in the B plus tree. Why? Because of the pointer nodes or nothing but address nodes. Again, next node should be the 31. Again 31. So here the overflow condition occurs. Again we have to go through the here. Let me see. Here the internal node is also overflowed when we take 17 to the up. So here 4 7 10 17 would be taken here. Here also it's occurred. Here 10 17 21 31. It should be occurred. But what we can do, here in the internal node also overflow occurs. Again we have to follow the same path. That means we have to take the left bias to the up. That means 7 goes to up, and then 4, and then 7 10 17. Again 1, here 4, here same 7 10 17 21 31. Here this is, but here we want to go on through the, we have to take one more step here. Here let me see, here 7 to 4, 4 to 1, 1 to 4. Actually this is all about the B tree insertion. Here 7 has 3 references here, so I directly deleted the middle reference, so we can save space, so directly it can be referred from here. Always all the data nodes must present at the leaf level. And also we have the property, leaf nodes are linked, all the leaf nodes remains at the same height, and every leaf node is equal distance from the root node. So we have to check whether this property is satisfied or not. Likewise the B plus tree creation goes on. This is all about B plus tree.